So we do a lot of building of databases, or I guess one building of databases, and like yeah, and connecting to other databases, and like I know I hear a bunch of terms being thrown around for like the different components of database internals. So I thought it would be great if we could go through and maybe outline what some of those internals are, and then give like a broader explanation of them.
Sure. So yeah. So yeah. Okay. So databases. So I guess like as a like introduction, like one of the reasons why I've always thought as a software engineer working on database engines has been sort of fun and instructive is that you sort of get inside of a database a sort of it's a very weird callback, but or oblique callback, but like databases are sort of a microcosm of computers and software as a whole, and I think that's both that's like an interesting framing, but also sort of databases sort of have to do a little bit of everything in order to do what they do. And to just sort of like give the one sentence, what is a database? I think about databases as systems which are responsible for persisting and returning previously persisted data to application code. And so there is, in my mind, though there's like a logical separation, if not actually a process or physical separation between application code, which is sort of supposed to be high level, and database code, which is generic to some extent and is concerned with just saving data and returning it efficiently. And classically, we run databases on separate systems, so their workloads can be isolated from application workloads. Databases are often provisioned more than provisioned differently than applications, such that many copies or instances of an application can run and communicate with a single database. A lot of database servers have sophisticated concurrency control systems, which means that multiple copies of the application can modify a single data or authoritative data, a piece of data at the same time without logically corrupting the data. Applications are responsible a little bit for like what is logical corruption in this case, and there are like a bunch of edge cases, but logically speaking, that's like what a database is. We have embedded databases which sort of provide that abstraction, but within a process. ClarityDB sort of works like that. SQLite is sort of the most sophisticated, prominent embedded database at the moment, though there have been many. And those have slightly different sort of parameters with regards to multi-process and concurrency. But these are just sort of like the examples. And databases, because they're sort of generic and meant to accommodate many different kinds of databases or different kinds of applications, we think about the like read and write workload on a database as sort of collectively the workload, and different kinds of databases are optimized for different kinds of write patterns and different kinds of read patterns and mixed patterns and data shapes, right? We see time series databases and graph databases, which mean that you have to lay data out very differently in order to efficiently return it. And also time series databases, for instance, have this ingestion problem where they have to potentially write a lot of data very quickly. So there's like a lot of like database, people have been making databases and been making different kinds of specialized databases in different ways for a long time. And so we sort of know like what it means to be a time series database or a graph database. There's also this category which ClarityDB and other engines like Redshift and Greenplum and Snowflake fall into, which is this analytics database, which are like generally speaking, databases with large volumes of data, with more frequent reads than writes, and large data volumes, read heavy, and maybe that's the thing. Oh, and most of the reads against analytics, sorry, brains, tend to be sort of aggregate, like aggregates of one kind or another, or sort of, taking a bunch of records and providing average values or of some kind of average, summation values. So that's databases, or that's like sort of like where databases are. And if there are sort of these like special data type databases, and there are analytics databases, the sort of core database that a lot of people think about are these transactional systems, which are about high throughput reads and writes to data that's changing more often, and where data there are correlated data changes, so that you have to change. I don't know if this is the term. If you correlated data changes is not a term of art, but you have to change value. A single change may involve like updating multiple values at once, and you need to be able to do that transactionally. So we call those OLTP, or online transaction processing systems. Oracle, Postgres, MySQL are the sort of classic OL and MS SQL and Sybase, etc. And DB2 are and MongoDB and some of the other NoSQL databases are classic OLTP systems. GlareDB is a classic analytics database, and other databases sort of usually fall in one place or another, in terms of like these kinds of transactions or analytics or specialized data types. So regardless of what kind of system or what kind of workload your engine's optimized for, we have a collection of parts. And this is sort of what you actually wanted me to talk about in the question. But the collection of parts is some sort of storage engine, which is like how you write data to disk, and a lot of transaction. The implementation of like writing transactions actually happens at a very low level inside of the storage engine typically. We'll get more into that. There is sort of at a slightly higher level the execution of the sort of higher level execution of write operations in your systems. A lot of databases, this is a sort of side component, but have indexes which are secondary copies of data that are more compact, and so therefore easier to keep in memory, that make it easier to narrow a search down to avoid needing to page lots of your sort of actual data into memory. So if you have indexes, which almost every database does, right, that there's this like layer on top of the storage, which is related, which is how do we like update indexes and implement transactions using the storage engine, and pipelining and stuff like that. On top of that, there is query execution and query, and there's sort of like there's a sort of stack of query kind of subsystems, including like the execution, which is sort of going through the data and producing the results. There is query planning and optimization, which is the process of taking a query, figuring out the most efficient way to execute the query, including which indexes to use, how do you sort of as a classic sort of compiler, how do you optimize a statement that a human wrote into the most easy and efficient to execute on a system. And this involves reordering certain operations or flattening parts of a query or selecting indexes for systems that have it. That's all sort of all in the query execution. And this is query. So like storage, in the way that this is a model for computers, the storage system is a lot like file systems work. The execution engine has a lot of like the execution, the write execution and the query execution have a lot of thread schedule, like scheduling, runtime properties. There's concurrency all over the place. Even embedded databases have like fairly involved concurrency models or constraints. And then queries in general are this like programming language and compiler problem, because you have to compile it and you have to execute it, and they're written as say what you will about SQL or any other query DSL, or domain specific language or query language, but it's a programming language, and you have to be able to handle that some way. Then on top of all of this, so this gives us, we have the programming language. There is this like language design part of query languages, and that's SQL, and how do we extend SQL, or how do we make it not SQL, depending on what your system needs are. You would think that because every SQL is standardized, that there wouldn't be a lot of programming language design problems, but there are, the like example that comes to mind is like Postgres wrote a bunch of, like, it's weird to say proprietary, but Postgres specific functions and operators for dealing with JSON documents or document types inside of SQL. So even SQL systems are sort of iterating on the language and building new tools, and they're not, well, like the core of SQL is standardized. Functions and special operators for special kinds of data aren't typically, and so people either copy some implementation that they like, or they YOLO it. I guess that's a sort of a generational identifier for me, but we'll ignore that. And then on top of all of this, you have queries. You're able to read and write data. There's a bunch of networking protocol stuff, like how do you handle connections, how do you there's a bunch of concurrency control here too. How do you handle the state of what a user is doing, right? If a user sort of sets a variable, where does that state live? And the answer is there are session objects, and we sort of store state where we have to or can, and there's this but there's also so state, the state management and serializing and deserializing data as it goes onto or comes off of the network. There are sort of at or above the networking labels authentication concerns, Some and many systems actually have a proxy or traffic or a router level. If you have the database, if your data is split up onto multiple servers, then you need a routing label or layer to direct queries to where they need to go, so that they can access the data that they need to access. And that also like gets into high availability. This is that where do you put the routing level is a sort of actually kind of big question. And sometimes you end up putting the routing level, you can sort of put it above or below the query engine, depending on like when you designed your system and what people were doing at that time. There are obvious arguments to both. And then this is actually the end, I promise. Now you have a sort of service which talks on a network protocol, which returns data. You have to have client libraries or libraries that run inside of applications which connect to the database and handle authentication and serialization and connection pooling, or not connection pooling, depending on your system. And so there is these like client libraries are either very simple, or you can actually, in some cases, systems will have client libraries that have a lot of distributed systems features. If some of that query routing level can actually be pushed onto clients, and not in every case, but some of those like higher level, like if you have like high availability systems implemented and distributed systems implemented in depending on what kind you have or what the design is, a lot of that work can actually happen in the client, and it's unintuitively slightly more efficient to do it that way, or it's easier for people to maintain. Jury's out on what the actual inspiration for that is, but that like those are sort of from a high level the parts of a database. We can go in and spend twice as much time on any given part, but that's it.
Let me try and just read it back quickly and make sure. It seems like there are basically 4 larger categories. So there's the storage engine, which is the file system. It's where everything is stored. That has maybe a subcomponent of like things like indexes, which make it easier to manage storage. After the storage engine, there's the query stack, which is like query execution, query planning and optimization, and then also like just the language design for the queries themselves. After that, you have all the networking and protocol stuff. So concurrency control, handling connections, managing user state, some amount of authentication, some amount of like routing if the data are split up in different places. And then after that, you have the client libraries, which are basically the user interface. So like how you actually will interface with the database from various applications. This also is going to have its own authentication concerns and also have to deal with serialization to get the data into or out of the application. Yeah, and these can be simple or more complex based on where concerns have been pushed. So maybe the distributed systems will be in the client library, but maybe they'll also be, I think, in the query execution.
Yeah, I mean, parts of that. I mean, there are sort of like I think storage engines are like interactions with the file system, but are sort of like the file system for the database. There's also this, but I think a lot of this also, there's also sort of a lot of this is that databases are sort of hot rods in a lot of ways, and so people who make databases want to be able to make it as fast as possible, and in order to do that, they have to have as much low-level control over memory management, file system access, networking access. And so if you were writing a web app, you say, or even a more complicated server or service, you might just sort of use the like nearest and best like HTTP server implementation. There are thousands of them. You pick one. You don't really have to think about networking. There's like, or networking protocol, because like they already have client libraries for HTTP. You don't think about that. But the kinds of data that databases are sending really and handling end up, in order to make it as fast as possible, to be the place where you push as much of your data manipulation workload onto the database, you really need it to be pretty fast. And because there are lots of different kinds of queries potentially targeting the same system, you have to be sort of efficient in a way that you might, and also like databases the thing that makes all databases fast is that the data that you need to use to access the data is small and fits in memory, and so you need control over the storage format or the intermediate formats or whatever it is, so that you avoid using more memory than you need to. You avoid you copying things until you absolutely need to. And you avoid reading, like the way to make avoid reading data into memory that you don't need to, because data sets are almost ideally almost always larger than the memory that you have. And so if you have a query that has to look at every single record in a database, it's going to be slow no matter what kind of system you have. There's no way to sort of beat physics sort of on that reality. But most of the time, even when you might not expect it, databases can sort of cheat for you, and be more efficient. So that's cool. And yeah, some of these higher order concerns depend a lot on what databases there are. Sometimes there's a couple of the storage, you can even imagine this, and some systems even do have a storage system and a query system that run in different processes and have some sort of network-based protocol. You can sometimes the routing layer is in different on different machines, on different servers entirely, and sometimes it's all part of the same sort of internal process. And so the marketing architecture diagram or hamburger visualization of how all of these parts fit together depends a lot on the system, or how we think about it, or how we've decided what kinds of tools, what the implementation is based on. And there are times when distributed systems features are in the client library, and there are times when they're hidden behind the server, and sometimes they're split a little bit. So there are a bunch of things that need to happen in order to use a database, and what kind of database it is, and how it's implemented, where the parts go where the actual code that runs any given part of this depends on sort of the specifics of the workload, the history of when the tools were written, what there are some patterns. People's all good ideas and some bad ideas are stolen repeatedly. So we see some common patterns, but